The Sun is the closest star to Earth and the central figure in our solar system. It's a massive sphere of hot plasma, about 100 times the diameter of Earth, and makes up more than 99% of the total mass in the solar system. Here are some fascinating facts about it. 1. Composition and structure. The Sun is composed mainly of hydrogen, about 74%, and helium, about 24%, with traces of other elements like oxygen, carbon, and nitrogen. It has several layers: the core, where nuclear fusion occurs; the radiative zone, where energy slowly radiates outward; the convective zone, where hot plasma circulates; and the photosphere, which is the visible surface. 2. Energy source and nuclear fusion. In the Sun's core, hydrogen atoms are compressed and fused to create helium, a process that releases enormous amounts of energy in the form of light and heat. This energy takes about 8 minutes to travel the 93 million miles, 150 million kilometers to Earth, a journey that makes it possible for life to exist. 3. Solar activity. The Sun has an 11-year solar cycle during which its activity rises and falls, affecting sunspots, solar flares, and coronal mass ejections. Solar flares and CMEs, coronal mass ejections, can impact Earth's magnetosphere, leading to phenomena like the auroras and, occasionally, disruptions in satellite and power systems. 4. Lifespan and evolution. The Sun is about 4.6 billion years old and has enough fuel to last approximately another 5 billion years. Eventually, it will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets, including possibly Earth. After shedding its outer layers, it will end its life as a white dwarf. 5. Influence on Earth and climate. The Sun's radiation drives Earth's climate and weather patterns. The tilt of Earth's axis and its orbit around the Sun are responsible for the seasons, while variations in solar energy affect long-term climate changes. The Sun is fundamental to life on Earth, providing the light and warmth necessary for photosynthesis, which supports almost all life on the planet. It's an object of immense study, as understanding its activity and behavior helps us protect our technology and understand the nature of stars across the universe. Certainly. The sun is so central to our existence that it's been a source of scientific fascination, cultural significance, and a focus of technological study. Here are some deeper insights. Hash 1. Nuclear fusion and energy output. The sun's core temperature is about 15 million degrees Celsius, 27 million degrees Fahrenheit. Here, intense gravitational pressure fuses hydrogen atoms to create helium, releasing energy through a process known as nuclear fusion. Every second, the sun converts about 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear bombs exploding simultaneously. SAR 2. Layers and solar atmosphere. The sun's atmosphere has three main layers beyond the photosphere: the chromosphere, the transition region, and the corona. The corona is particularly intriguing because it is much hotter than the sun's surface, reaching temperatures up to 1 to 3 million degrees Celsius. Scientists still study why the corona is so much hotter, a mystery known as the coronal heating problem. NER 3. The solar wind. The sun constantly emits a stream of charged particles known as the solar wind, which flows through the solar system and interacts with planetary magnetospheres. On Earth, the solar wind is largely deflected by our magnetic field, but during intense solar storms, it can penetrate deeper, causing geomagnetic storms, auroras, and disruptions to GPS, communication satellites, and power grids. 4. Sunspots and solar cycles. Sunspots are cooler, darker patches on the sun's surface caused by intense magnetic activity. They are often precursors to solar flares and CMEs. The 11-year solar cycle influences the number of sunspots and the intensity of solar activity. During solar maximum, there are more sunspots and solar storms, while during solar minimum, activity is reduced. Hatter 5. The role of the sun in understanding the universe. The sun is a G-type main sequence star, or G-dwarf. Studying the sun helps astronomers understand the life cycles of similar stars and contributes to stellar physics. Observing the sun's spectrum led to the discovery of helium, an element first identified in the sun before it was found on Earth. 6. The sun's magnetic field. The sun's magnetic field is highly dynamic, constantly shifting and twisting due to the movement of plasma within it. Every 11 years, the sun's magnetic field undergoes a complete polarity reversal, swapping the positions of its magnetic north and south poles. This contributes to the solar cycle and the variation in solar activity. 7. Solar observatories and space missions. Missions like NASA's Parker Solar Probe and the ESA NASA Solar Orbiter are designed to study the sun's outer layers and the solar wind up close. Ground-based observatories like the Daniel K. Inouye Solar Telescope provide high-resolution images of the sun, allowing us to study its surface features and understand magnetic phenomena. 8. The sun in human culture and mythology. The sun has been worshipped and revered in countless cultures. Ancient Egyptians worshipped Ra, the sun god. The Aztecs believed the sun needed human sacrifices to sustain its journey. And many other societies built solar calendars, like Stonehenge, to track its movement. Modern calendars, timekeeping systems, and even the concept of a year are based on Earth's orbit around the sun, showing how much of human culture is tied to it. The sun is far more than just a source of light and warmth. It's a powerhouse that drives planetary climates, influences technology and space travel, and continues to inspire both scientific research and cultural fascination. The sun is a fascinating and complex celestial object, influencing not only our solar system, but also advancing our understanding of astrophysics. Here are some more detailed insights into the sun's impact, structure, and mysteries. 1. The sun's dynamic surface and granulation. The visible surface of the sun, or the photosphere, is covered in a pattern called granulation. These are tiny cells, each about 1,000 kilometers across, where hot plasma rises and cools as it radiates energy outward. Each granule lasts only about 8 to 20 minutes, constantly shifting as the sun's boiling plasma behaves like a bubbling pot of water. 2. Spectroscopy and element discovery. Spectroscopy, the study of light spectra, has allowed scientists to identify elements in the sun and other stars by observing the unique signatures in their light. The element helium was discovered in 1868 by astronomer Jules Janssen, who observed a yellow line in the sun's spectrum that didn't match any known element at the time. It was later confirmed and named after Helios, the Greek god of the sun. 3. The sun's gravity and the solar system's structure. The sun's immense gravitational pull holds the planets, moons, comets, and asteroids in orbit. Without it, the planets would drift away into space. This gravitational force also governs the orbits of distant objects in the Kuiper Belt and Oort cloud, regions full of icy bodies and comets, extending the sun's influence far beyond the known planets. 4. Solar flares and space weather. Solar flares are intense bursts of radiation caused by the release of magnetic energy from sunspots. They can accelerate particles to near light speeds and release energy equivalent to millions of hydrogen bombs. These flares contribute to space weather, which has practical implications on Earth. Solar flares can disrupt radio communications, GPS signals, and even cause damage to satellites and astronauts in space. 5. The solar dynamo and magnetic field generation. The sun's magnetic field is generated by a process called the solar dynamo, created by the complex movement of charged particles within its interior. As plasma in the sun rotates at different speeds, faster at the equator than at the poles, it twists the magnetic field lines, which eventually snap and reconnect, creating phenomena like sunspots, solar flares, and CMEs. 6. Solar oscillations and helioseismology. The sun experiences oscillations or sound waves caused by convection in its outer layers. By studying these oscillations, a field called helioseismology, scientists can infer details about the sun's interior, much like seismologists study earthquakes to understand Earth's structure. These oscillations help map features deep within the sun, providing insights into temperature, density, and flow patterns in layers we can't observe directly. 7. Coronal mass ejections, CMEs, and their impact on Earth. CMEs are huge clouds of plasma and magnetic fields that the sun ejects during periods of high solar activity. They can carry billions of tons of charged particles and travel at speeds up to 3,000 kilometers per second. When a CME collides with Earth's magnetic field, it can trigger geomagnetic storms, resulting in auroras and potential disruptions to technology, including satellite malfunctions, power grid failures, and increased radiation for high-altitude flights. 8. The solar system's solar bubble, the heliosphere. The heliosphere is a vast bubble of solar wind extending far beyond the outer planets, creating a boundary with interstellar space called the heliopause. The Voyager 1 and Voyager 2 probes have passed through this boundary, providing the first direct measurements of interstellar space, revealing the sun's protective shield against cosmic rays and interstellar particles. Future of solar observation and research. New missions like the European Space Agency's Solar Orbiter and NASA's upcoming projects aim to gather high-resolution data on the sun's poles and inner corona. Advanced solar telescopes like the Daniel K. Inouye Solar Telescope in Hawaii are capturing the most detailed images ever taken of the sun's surface, helping scientists understand its magnetic field dynamics and sunspot formation in detail. 10. Impact of the sun on planetary atmospheres and potential habitability. The sun's ultraviolet radiation is essential for planetary atmospheres. For Earth, it breaks down oxygen molecules, forming ozone, which protects life from harmful UV rays. Solar radiation and solar winds can strip away planetary atmospheres if a planet lacks a protective magnetic field. Mars, for example, lost much of its atmosphere over time due to the sun's solar wind, affecting its potential for habitability. The sun, though an ordinary star in the cosmic scale, is central to every aspect of life and science in our solar system. Its magnetic storms and vast corona, along with future discoveries, ensure that we're only beginning to unlock the mysteries of this powerhouse. Each mission and an observation brings new insights into not only the sun, but also stellar physics, helping us better understand other stars across the galaxy. Absolutely. The Sun is an incredibly complex star with characteristics and behaviors that continue to intrigue scientists. Here's more on some of the less commonly known aspects of our Sun. 1. Neutrinos, the Sun's ghost particles. The Sun produces vast amounts of neutrinos, nearly massless particles that are created during nuclear fusion in the core. These ghost particles travel at nearly the speed of light and barely interact with matter. Billions of neutrinos pass through every square inch of Earth and our bodies every second, but they are almost undetectable. Special detectors deep underground, like the Sudbury Neutrino Observatory in Canada, are used to capture a few of these elusive particles to study the processes within the Sun's core. 2. The Sun's color and why it looks yellow. Despite appearing yellow from Earth, the Sun actually emits white light, a combination of all visible colors. The atmosphere scatters shorter blue and violet wavelengths, so we mostly see yellow-orange hues. From space, without atmospheric filtering, the Sun would appear closer to pure white. 3. The solar heartbeat. The Sun experiences a roughly 11-year solar cycle that acts like a magnetic heartbeat. During this cycle, the number of sunspots, dark, cooler patches on the surface, fluctuates, and the Sun's magnetic poles flip. The solar cycle impacts space weather, with increased sunspots leading to more frequent solar flares and coronal mass ejections. At the height of the cycle, solar maximum, auroras are more common, and the Sun's activity can interfere with satellite and communication systems. Number 4. The Parker Spiral, the Sun's magnetic field in space. The Sun's magnetic field extends far beyond the Sun itself, influenced by the solar wind. As the Sun rotates, its magnetic field twists into a spiral pattern known as the Parker Spiral, named after physicist Eugene Parker. This spiral shape impacts the entire solar system, guiding charged particles and influencing the paths of cosmic rays and interplanetary magnetic fields. It also plays a role in shaping planetary magnetospheres, like Earth's magnetic field. Hash number 5. Spicules, the Sun's plasma jets. Spicules are short-lived, jet-like eruptions of plasma that shoot up from the Sun's surface into the lower corona at speeds of up to 150,000 kilometers per hour. These jets, which can last from a few minutes to a few hours, contribute to coronal heating, although scientists are still investigating how spicules might transfer energy from the surface into the much hotter corona. 6. Coronal loops and magnetic reconnection. Coronal loops are large, arching structures of plasma held in place by magnetic fields. They are visible during solar flares and can sometimes extend thousands of kilometers above the solar surface. These loops can undergo magnetic reconnection, where twisted magnetic fields snap and reconnect, releasing massive amounts of energy. This phenomenon is a major cause of solar flares and coronal mass ejections. Number 7. The heliosphere and cosmic ray shielding. The heliosphere, a vast bubble created by the solar wind, acts as a shield against cosmic rays, high-energy particles from outside the solar system. Cosmic rays are potentially harmful to both technology and biology, so the heliosphere's shielding helps protect planets like Earth from this radiation. During solar maximum, when the Sun is more active, the heliosphere expands, providing even greater protection against cosmic rays. 8. Solar twins and stellar comparisons. The Sun has solar twins, stars with similar size, mass, and luminosity. Studying these twins, such as 18 Scorpii, helps scientists understand more about the life cycles and behavior of stars like our Sun. Observations of younger or older solar twins give insights into the Sun's past and future, helping scientists predict what might happen as our Sun ages, transitions to a red giant, and eventually becomes a white dwarf. 9. The Sun's role in the faint young sun paradox. The Sun has gradually increased in brightness over billions of years. During Earth's early history, the Sun's luminosity was about 30% lower than it is today, which should have made Earth too cold for liquid water. However, geological evidence suggests that liquid water existed early in Earth's history. This faint young sun paradox is still a puzzle for scientists. Some theories suggest greenhouse gases helped warm early Earth, or that other factors in the young solar system contributed to Earth's warmth despite the faint sun. 10. Solar holography, probing the Sun's hidden face. Solar holography is a technique used to study areas of the Sun that aren't directly visible from Earth, such as the side currently facing away from us. By analyzing vibrations on the sun's surface, scientists can create holographic images of its far side, allowing for the prediction of new sunspots or active regions that might rotate into view in the coming days. This technique helps in forecasting space weather. 11. Solar flares and their classification. Solar flares are categorized into classes A, B, C, M, and X, with X class flares being the most powerful. An X10 flare, for example, is 10 times stronger than an X1 flare. These intense flares are capable of releasing as much energy as billions of atomic bombs, with potential to cause radio blackouts, GPS malfunctions, and auroras on Earth. 12. The death of the sun. What happens next? In about 5 billion years, the sun will run out of hydrogen in its core. It will expand into a red giant, possibly engulfing the inner planets, including Earth. After shedding its outer layers, the sun will leave behind a dense core known as a white dwarf, roughly the size of Earth, but with about half the sun's current mass. This white dwarf will cool over billions of years, gradually fading until it no longer emits visible light. The sun, as a relatively ordinary star, is a perfect laboratory for understanding the life cycles of stars and the dynamics of stellar phenomena. Each discovery about our sun deepens our understanding of stellar physics, space weather, and even the potential for habitability on planets orbiting distant stars. Absolutely. There's always more to explore about the sun. Here are some additional fascinating and complex aspects of our star. 1. The solar atmosphere's supergranules. The sun's surface has a distinct pattern called supergranulation, composed of cells much larger than ordinary granules. Each supergranule spans around 30,000 kilometers and lasts longer, sometimes up to 24 hours. Supergranules are sites of intense magnetic activity, and their flow patterns contribute to the sun's complex magnetic field and help to transport magnetic elements across the sun's surface. 2. The solar cycle and its impact on Earth's climate. While the sun's energy output remains mostly stable, tiny fluctuations tied to the 11-year solar cycle can impact Earth's climate. During periods of high solar activity, the increased ultraviolet radiation heats Earth's upper atmosphere, which can subtly affect weather patterns. While these changes are small compared to human-driven climate factors, studies have linked the sun's activity to certain historical climate events, such as the Little Ice Age from the 14th to the 19th century, which coincided with a period of low solar activity known as the Maunder minimum. Hammer 3. Solar minimums and maximums, extremes of the solar cycle. During a solar minimum, sunspots and solar storms are rare, and the sun's magnetic field is relatively quiet. However, during a solar maximum, sunspots and solar flares are frequent, leading to more intense space weather. Solar maximums increase the likelihood of CMEs, which can create beautiful auroras but also pose risks to modern technology. The largest recorded CME, known as the Carrington event of 1859, caused auroras visible near the equator and sparked fires due to telegraph sparks. If a similar event occurred today, it could disrupt power grids and satellites worldwide. Number 4. Solar switchbacks, mysteries uncovered by Parker Solar Probe. NASA's Parker Solar Probe, launched in 2018, discovered strange magnetic switchbacks in the solar wind near the sun. These are rapid reversals in the magnetic field direction, and scientists are still trying to understand their cause. One theory is that they're caused by turbulence in the sun's outer atmosphere, potentially linked to the sun's magnetic reconnection process. These switchbacks may play a role in heating the solar corona and accelerating the solar wind. 5. The sun's differential rotation. The sun doesn't rotate as a solid body. Instead, it has differential rotation, meaning its equator and poles rotate at different speeds. The equator completes a rotation in about 25 days, while the poles take about 35 days. This differential rotation twists the sun's magnetic field over time, contributing to the formation of sunspots and influencing the solar cycle. The resulting magnetic stress plays a big role in creating solar flares and CMEs. 6. The chromosphere. The sun's colorful. Above the photosphere lies the chromosphere, a layer about 2,000 kilometers thick, which is visible as a reddish ring during solar eclipses. The chromosphere is the region where the temperature of the sun begins to rise again after decreasing outward from the core, climbing from around 4,500 degrees Celsius in the photosphere to as much as 20,000 degrees Celsius in the chromosphere. This temperature rise contributes to phenomena like spicules and the heating of the corona. 7. Magnetic carpet of the sun. The sun's surface is covered in a magnetic carpet, a web of small magnetic loops that are continually shifting and changing. Each magnetic loop ranges from a few hundred to a few thousand kilometers and is fueled by the dynamic movements in the sun's convective zone. Scientists believe the constant reconfiguration of this magnetic carpet might help heat the corona and explain why it's much hotter than the photosphere. 8. Helioseismology, the study of solar quakes. The sun has its own version of earthquakes, known as solar oscillations. By studying these sound waves which bounce around inside the sun, scientists can learn about its internal structure. Helioseismology reveals details about the sun's temperature, composition, and even the speed of rotation at different depths. It has shown, for example, that the core rotates faster than the outer layers, offering insights into how energy moves within the sun. The coronal heating mystery. Why the corona is hotter than the surface. The corona is millions of degrees hotter than the photosphere, an anomaly that defies traditional understanding of heat transfer. Two leading theories are magnetic reconnection, where magnetic fields break and reconnect, releasing energy, and alpha waves, waves in the sun's plasma that might transfer energy to the corona. Understanding coronal heating isn't just about solving a mystery. It has practical applications for understanding other stars, stellar evolution, and the mechanics of magnetized plasmas. 10. The ongoing threat of solar superflares. Although rare, stars like the sun can produce superflares, thousands of times more powerful than typical solar flares. Observations of distant solar analogs suggest that even a relatively stable star like our sun could theoretically produce a superflare. If a superflare hit Earth, the results could be catastrophic for our electrical infrastructure, communication systems, and satellite networks. While scientists estimate the likelihood of such an event as low, ongoing solar observation helps monitor such risks. 11. Stellar evolution pathways, the sun's unique journey. The sun is classified as a G-type main sequence star. Stars like the sun follow a predictable life cycle, fusing hydrogen into helium for most of their lives before expanding into red giants. At the end of the red giant phase, the sun will shed its outer layers, creating a planetary nebula before settling into a white dwarf. This final remnant will eventually cool and fade over billions of years, quietly marking the end of our sun's life cycle. 12. Interstellar impact of the sun's end, creating cosmic dust. When the sun reaches the end of its life, it will release materials into space that will contribute to cosmic dust, the building blocks for future stars and planets. This material could eventually become part of new solar systems. In this way, the sun's life cycle contributes to the recycling of stellar materials in the galaxy, providing elements essential for the formation of planets and possibly life. The sun is both our life-giving star and a vast, complex system that continues to be a puzzle for scientists. As we develop better technology to study it up close, such as solar probes and high-resolution telescopes, we're likely to uncover even more fascinating and unexpected aspects of this star that illuminates our solar system.